Hello, ladies and gents. This time we're going to talk about the pH scale and what do the numbers pH stand for and what do they actually mean. So first off, the abbreviation pH stands for potential hydrogen. And this is a convenient way to express how acidic or how basic a solution is. The pH scale ranges from 0 through 14. Neutral is 7. A nice pure sample of water is going to have a pH of 7. And then anything with a lower pH than 7 is going to be acidic, and anything with a higher pH than 7 is going to be basic. And as you get to the more extremes on both levels, you're going to get things that are much more basic and much more acidic. Now, you may have looked at this and said, why in the world is a pH of 7 neutral? It's not an incredibly obvious answer. I remember looking at this in my past and thinking, what goofball created this system? Because it's not logical. The Celsius scale makes sense. You know, you had 0 to 100 and yeah, okay, divide that up into 100 pieces, boiling and freezing point of water. There are 1,000 milliliters in a liter. Okay, I buy that. That makes sense. There's 100 centimeters in 1 meter. I can even buy a football field that there are 100 yards and they call the middle the 50-yard line, and it goes to 0 as you go to both goalposts. That makes sense too. But if you look at something that is based on nature, like how many days in a year, it's 365 and a quarter days for the Earth to actually orbit the sun. It's such a wacky number because it's based on something that's actually observed in nature. Well, that's exactly the same reason why a pH of 7 happens to be neutral. So to explain why this is, we have to remember a couple things we've talked about in the past. Water is an amphoteric compound. That means that water can be an acid when it produces hydronium ions, and water can be a base or act as a base when it produces hydroxide ions. Water is a very special compound in chemistry and in life for so many reasons. Now, one of the interesting things is if you take a sample of pure water, at any moment in time, some of the molecules of water are going to be ions, not molecules. If you take a 1 liter container full of water, within that 1 liter container, a very, very, very small number of those water molecules are going to be broken down into ions. Matter of fact, in 1 liter of water, 1 times 10 to the negative 7 moles per liter are going to be hydronium ions, which are the ones that indicate an acid. And in that same liter, 1 times 10 to the negative 7 moles per liter are going to be hydroxide ions, which indicate if something is a base. So look at this number 7. That starts to give us a clue why neutral water is 7. This is the official definition of pH. So put a big star by this. This is something important to know. pH is defined as the negative logarithm of the hydronium ion concentration of a solution. pH is the negative logarithm of the hydronium ion concentration of a solution. This is the mathematical equation that is used to calculate pH. Now, if you look at that and you go, ugh, logarithms and math equations, don't worry about it. We're going to spend a lot of time for the rest of this week and some time next week trying to make sense out of what this means. Now, pH actually stands for potential hydrogen. In Mary's little wacky brain, I think of it as parts hydronium. It's not official. It's not actually what pH stands for, but I think of it that way because it has to do with the concentration of hydronium ions in a solution. So we want to know how many moles of hydronium are going to be in a liter of solution. And we've talked about concentration in the past. So let's go through some examples. Let's say I had 1 liter of water. And I put bottled water up here, but I'm talking actually about distilled or deionized water. And if I had 1 liter of pure water, in it, there would be 1 times 10 to the negative 7 moles of hydronium ions. So the concentration, looking at this equation, would be 1 times 10 to the negative 7 moles per liter. Now, if we go back to our equation for molarity, moles per liter, that would be the concentration, the molar concentration of hydronium ions inside our pure sample of water. Now, how do we go from this to pH? Next week, we're going to do the real math, but what I'm going to show you this week is the quick and dirty method, because this week I care that you get the idea. We'll worry about the mathematical stuff next week. This week's all about the idea. So here's the quick and dirty method. If you look just at the power of 10, if you take that power of 10 and you change the number from being negative to positive, that's going to be the pH. And so that power of 10, 7, change it from negative to positive, and that's the pH of my solution. This works for whole numbers like 7, 8, 9, and 10. When we get non-whole numbers, then we're going to have to do real math. Let's try another one. Milk, if I have a liter of milk, the concentration in that solution is going to be 1 times 10 to the negative 6 moles per liter of hydroniums. So what's going to be the pH of that solution? Again, quick and dirty method is we're going to take that power of 10, switch it from negative to positive, the pH is 6. And if you look on my chart, neutral water has a pH of 7. Milk is slightly acidic, and it has a pH of around 6. Let's take a look at something that is basic, and a common base that many of you have in your home is baking soda. Now, baking soda has within it, if we had a baking soda solution, 1 times 10 to the negative 8 moles per liter. And the quick and dirty method of finding pH, we change this from a negative to a positive, so the pH of baking soda solution is going to be 8. Baking soda, here is my 7. This chart says it's 9. Kind of depends on which source you look at, but let's say that this is going to be a little bit more basic than my neutral water. We're in the base direction, and that's the pH of my baking soda. Try this on your own. Okay, what's the pH of coffee? Easy. Negative 5 turns into 5. And so coffee is much more acidic than pure water, and it's more acidic than milk. Let's try another one. Tomato juice. All right, tomato juice. Tomato juice, 1 times 10 to the negative 4th. Change that from negative 4 to 4. That's the pH of tomato juice. So tomato juice is more acidic than black coffee, and more acidic than milk, and more acidic than water. And this is all related to the thing I really want you to understand is pH is related back to the concentration of how many hydronium ions there are in a liter of solution. It's based on counting those ions, counting a concentration. Now, pH is wacky because it's a logarithmic scale. Now, what that means is when the pH value changes by 1, that means there's a 10 times increase in the number of hydronium ion concentration. So the difference between water, 1 times 10 to the negative 7, and milk, 1 times 10 to the negative 6, this number, because these are negative exponents, this actually means 10 times more hydronium ions in the milk in the same volume than water. For coffee, 1 times 10 to the negative 5, well, compared to milk, that's again 10 times more. And for tomato juice, again a negative exponent, 1 times 10 to the negative 4. These numbers, believe it or not, are getting bigger. They are getting larger. They are also getting more acidic because the hydronium ion concentration is going up. So each one of these is a 10 times jump. But if you look at a bigger jump from water down to coffee, it's 10 times to milk and 10 times to coffee. And what is 10 times 10? Well, 10 times 10 is 100 times. But if we make another jump, let's say we go water to tomato juice, that's going to be 10 times 10 times 10. 10 times 10 is 100, times 10 is 1,000. So water down to tomato juice, the difference is 1,000 times more acidic the tomato juice is than pure water. Logarithmic scales are weird and crazy things, and they're very hard for us to wrap our heads around because of the fact that we don't use them often. Let me give you an analogy. And the analogy I'm going to use is shopping. Why? Because we all shop. I love to shop, quite honestly. And I'm going to talk about buying shoes because my husband teases me that I have way too many shoes. So let's say you find a fun pair of shoes and you think the tag says 20. And when you get to the register, it says 30. Well, if you really love the shoes, you are in shoe love, difference between 20 and 30, you probably are going to go, oh, I love the shoes, I'm going to buy them anyhow. That's normal decimal math. 20, 30, okay, yeah, it's $10 more, but it's not going to probably be the end of the earth if it's 20 to 30. And if you are in real shoe love, you're just going to go for it and da-da-da, that's the way it works. But when you're dealing with logarithm math, things are wacky. If the tag said 20 and you get to the register and the salesperson said it really is 30, if it's logarithms, the difference between that 2 and the 3 means 10 times more. And so instead of the shoes costing $20, they're going to cost $200. And you're probably going to go, wah, wah, wah. I'm not going to spend $200 on a pair of sandals. That's just wacky. This is so unusual because in our normal life, we do not deal with logarithm math very often. And that's one of the reasons why pH and the concept of pH is difficult, because it's very unusual kinds of math. There are two other logarithmic scales you're going to encounter in your life. One of them is the Richter scale. The Richter scale is used for earthquakes. If you have an earthquake of an 8 versus an earthquake on the Richter scale that is a 7, that means that the Richter scale earthquake of an 8 is 10 times more powerful than the earthquake at a 7. Or the earthquake at an 8 happens to be 100 times more powerful than an earthquake at a 6. Decibels is another logarithmic scale that you may have heard of. This is what's used for sound level. And decibels, they add an extra 0 in there, but the idea is still the same. So if you have a sound at 70 decibels and another sound at 80 decibels, the difference between the 80 and the 70, 80 is 10 times more. But if you have a 90 dB sound, that 90 dB sound is going to be 10 times more than the 80, but the difference between the 70 and the 90 is 100 times more powerful than the 100 times more power it can actually damage your eardrums. These are wacky scales, the math is unusual, and it's difficult on us mere mortals. So, one number difference in pH, 10 times more acidic or 10 times more basic. We're going to leave this talk right here, and we're going to come back right here when we start pH part 2. See you then. Bye-bye.